What if the universe doesn't end in fire, but in absolute nothingness? We often imagine the end of all things as a cataclysmic explosion, a grand finale filled with sound and fury. But the truth of cosmic destiny might be far stranger, and honestly, far quieter. It might be a slow, creeping silence that eventually swallows everything. The stars will not explode in a final glorious burst. Instead, they will simply fade away, one by one, until only an endless, cold and empty void remains. This is not a story of a bang, but of a final, lingering whisper that fades into an eternal, unchanging darkness. It's a chilling thought, but one that modern cosmology actually forces us to confront as we peer deeper into the fabric of reality. Imagine the universe as a grand, roaring bonfire. In its youth, it burned brightly, forging stars and galaxies in a brilliant display of creative energy. But all fires eventually run out of fuel. The Big Freeze, or heat death, is the theory that describes this slow, inevitable cooling. It's not a dramatic event, but a gradual process of entropy taking over. The second law of thermodynamics, a fundamental rule of physics, states that in a closed system like our universe, entropy always increases. The universe is expanding, and that expansion is accelerating due to a mysterious force called dark energy. Future civilizations, if any exist, will look out into a sky that appears completely empty beyond their own local group of stars. Sun-like stars will swell into red giants and then fade into cold, dead white dwarfs. Massive stars will explode as supernovae, leaving behind neutron stars or black holes. Even black holes, the universe's ultimate prisons of matter and energy, will eventually evaporate through a process known as Hawking radiation, first proposed by the brilliant physicist Stephen Hawking. After an unimaginable length of time, the universe will reach a state of maximum entropy, a vast, cold, dark, and perfectly uniform void where nothing ever happens, forever. If the Big Freeze is a slow, quiet death, the Big Rip is its terrifyingly violent opposite. This theory proposes an end where the very fabric of the universe is torn to shreds. The culprit once again is dark energy, but a particularly aggressive form of it known as phantom energy. It's like pressing the accelerator on a car and finding that the pedal is pushing back, forcing you to go faster and faster. The Milky Way itself would be torn apart, its stars flung into the rapidly expanding void. We would watch as neighboring stars, once familiar points of light in our night sky, accelerate away from us at impossible speeds, disappearing from view. The Earth would be ripped away from the sun, and all the planets would be sent hurtling into the darkness. The Earth itself would explode. Buildings, mountains, and oceans would all disintegrate into a cloud of unbound atoms. Every atom in the universe would be ripped apart into its constituent quarks and leptons. Space-time itself would be torn asunder, and the concept of distance would lose all meaning. The universe would end not in a freeze or a crunch, but in an infinitely fast, infinitely violent dissolution of everything. This theory is perhaps the most unsettling of all because it could happen at any moment without any warning. To understand it, think of the universe as being in a state of energy, like a ball resting in a valley. What if our universe is actually like a ball resting on a small ledge on the side of a much deeper valley? The laws of quantum mechanics allow for a phenomenon called quantum tunneling. If this were to happen somewhere in the cosmos, it would create a bubble of true vacuum. It would expand outwards in all directions at the speed of light. One moment, everything would be normal. The next, the wall of the bubble would arrive and obliterate everything it touches, rewriting the laws of physics as it passes. Current measurements from facilities like the Large Hadron Collider suggest that our universe is metastable. A bubble of true vacuum could have already formed in a distant galaxy and be hurtling towards us right now, an unstoppable wave of cosmic annihilation set to arrive without any notice. For much of the 20th century, the leading theory for the universe's end was, well, a perfect mirror image of its beginning. If the universe started with a Big Bang, an explosive expansion from a single point, perhaps it would end with a big crunch, a catastrophic collapse back into a single point. This idea, has a certain poetic symmetry. The cosmic story would be a grand cycle of expansion and contraction. In a big crunch scenario, the accelerating expansion we see today would eventually slow down. It would halt. And then, it would reverse. Galaxies would stop rushing away from each other and would begin to fall back together. The night sky, which is currently growing darker and emptier, would instead become brighter and brighter. The final stages of the Big Crunch would be a fiery inferno. Stars would be unable to radiate their heat away, and would begin to cook from the outside in, eventually exploding. The end of the Big Crunch is a singularity, a point of infinite density and temperature, just like the one that, in theory, existed before the Big Bang. What if the singularity of the Big Crunch isn't an end, but a new beginning? This is actually the central idea behind the Big Bounce theory, sometimes called the oscillatory universe model. A Big Bang leads to a period of expansion, which is eventually halted and reversed by gravity, leading to a Big Crunch. But instead of collapsing into an infinitely dense point of no return, the universe bounces. So our cosmos would be just one iteration in an endless chain of universes. It transforms the single, linear story of our cosmos into an epic, cyclical saga of cosmic death and rebirth. One leading idea, called loop quantum cosmology, suggests that space-time itself is made of discrete, indivisible loops or atoms of space-time. Instead, when it reaches that maximum density, a powerful repulsive force, a kind of quantum pressure, pushes back, forcing the universe to rebound into a new Big Bang. However, the Big Bounce has, well, fallen out of favor with many cosmologists, mainly due to the 1998 discovery that the universe's expansion is accelerating. Nevertheless, the idea remains a compelling and philosophically satisfying alternative to a universe with a definitive final end, offering a vision of eternal recurrence rather than ultimate oblivion. The discovery of dark energy in the late 1990s, led by teams including Saul Perlmutter, Brian Schmidt, and Adam Rees, completely revolutionized cosmology. It earned them the Nobel Prize in Physics and revealed that about 70% of the universe is made of this mysterious substance that drives cosmic acceleration. But here's the secret. We have almost no idea what it is. Imagine dark energy as a dynamic field that can change its value, something physicists call quintessence. If this field were to slowly lose energy, its repulsive force would weaken. Conversely, what if the dark energy field gains strength over time? This is the phantom energy that leads to the Big Rip. We are like ancient mariners who have just discovered the existence of ocean currents but have no idea where they lead. We're building new observatories like the Vera C. Rubin Observatory and the Euclid Space Telescope, specifically designed to map the expansion history of the universe with unprecedented precision. Let's return to the Big Freeze scenario, which is, honestly, the most widely accepted fate based on current data. Trillions of years have passed. All the stars have burned out. All matter has decayed. In this distant, dark future, the last surviving celestial objects will be black holes. As Stephen Hawking brilliantly theorized in 1974, black holes can evaporate. This process, known as Hawking radiation, is a consequence of quantum mechanics near the event horizon, the black hole's point of no return. In the very last second of its life, it will release a final brilliant burst of gamma rays, a last flicker of light in the infinite darkness. And then, once the last black hole has evaporated, that's it. The universe will finally reach its true state of heat death. So we return to our initial question. What if the universe ends not in fire but in nothingness? As we have seen, whether through a slow freeze, a violent rip, or a sudden bubble of decay, the ultimate fate of the cosmos appears to be oblivion. We are living in the stelliferous era, the glorious star-filled springtime of the cosmos. Our existence is a remarkable, improbable gift. In a universe governed by entropy and destined for decay, the emergence of order, complexity, and consciousness on this small planet is nothing short of a miracle. We are the universe's way of observing itself, of understanding its own story, however brief that story may be. The meaning of our lives is not found in some guarantee of cosmic permanence, but in the experiences of this moment, in our capacity for love, for discovery, for art, and for compassion. The ultimate end of everything is a story that is still being written, and we are the ones holding the pen, trying to decipher the clues. Our lives may be a brief flash of light, but we have the extraordinary privilege of being here to witness the grand spectacle of the cosmos. To ask these ultimate questions, and to appreciate the beauty of our ephemeral, brilliant, and ultimately finite universe.